Ancient civilizations are renowned for their sophisticated calendar systems, like the Chinese calendar, which is still in use today. Back then it was a pretty big deal to know the correct time of year, either for growing your crops or navigating the sea. The calendars often had a complex system of rules, employing intricate mathematical operations. But not everyone was a genius who could compute this in a span of less than 5 seconds. So the brains of the time wanted to make another brain that could do these annoying, but essential calculations for them. In other words, that meant bringing the math to life, which is arguably just physics in action. Mathematical notions could be interpreted by a number of physical devices such as the pendulum or a complex collection of gears, like the ones found in this thing which the Greeks used to track the Olympic Games. This, depending on your definition, can be said to be the world's first analog computer, that is, a computer that represents or processes its information through a continuous variation in physical quantities. This watch, for example, is an analog mechanism that is still in use today. For a long time, calculations didn't get much more complicated, and even if they did, there was hardly any practical need for these calculations. The delicate engineering of the Antikythera was virtually unmatched, at least until the Renaissance and subsequent scientific revolution. After a long hiatus in Europe, mathematics and science in general made an explosive comeback, where entire fields like calculus emerged out of nowhere. While Newton also created calculus, the symbols that you now see in your textbooks are the works of German polymath Gottfried Leibniz. So what does Leibniz have to do with our story? Well, among his children was the binary system, which is responsible for you watching this video today. Inspired by the Chinese I Ching, which comprises broken and unbroken lines, Leibniz formulated a system in which all numbers in the universe could be represented by a certain number of zeros and ones. These are the rules for conversion. Or just go here instead. It wasn't only numbers that could be represented by Leibniz's system, but also opposite pairs like yes or no, on or off, and most importantly true or false, which is the cornerstone of George Boole's algebra, or Boolean algebra, for short. Although computers weren't so eager to adopt this logic, monumental stepping stones were being laid. Innovators like Charles Babbage started building their computers to operate in discrete steps, greatly increasing accuracy and utility. This was achieved by a system of gears and levers, where each gear would represent a digit. For the sake of convenience, these first mechanical computers were based on the decimal system, like this one for example. However, as you can tell, decimal wasn't exactly the best choice, and even Leibniz knew about this. While building the Leibniz mechanical calculator using decimals, he foresaw the supremacy of the binary system, which was formalized by Claude Shannon in the late 30s with the help of Boolean algebra. Simply put, this is 1 and means true, and this is 0 and means false. For this reason, Shannon is often referred to as the father of the information age, in addition to having an AI named after him. Great idea. Let's add some quantum spookiness to the business of computing. I forgot to tell you that the basic unit of information is the bit, which has a value of either 0 or 1, like I said. How about both? This is the basis of quantum computing, where instead of a bit you have a qubit, which exists in a superposition of 0 and 1. Therefore, unless it is measured, a qubit will simultaneously be 0 and 1 at the same time, although the possibilities can be unequal. This idea is inspired by the behavior of matter at the smallest scale, hence quantum. Take light, specifically visible light for example. In certain contexts it is a wave, specifically a rather timid member of the electromagnetic family. In other cases, like the one that won this guy his 1921 Nobel Prize, light is a particle that slams electrons and removes them from metal surfaces. This is the famous wave-particle duality, which technically applies to everything including you, but is shown by de Broglie's formula to be much more pronounced when considering very small entities, like the electron. At the current moment, quantum computing remains largely impractical, with large-scale implementation proving difficult to achieve. For a quantum computer to work properly you must ensure that its qubits are perfectly isolated from any outside influence. At the quantum level even tiny disturbances can undo the qubit-specific superposition, forcing it to behave more classically and therefore, defeats the purpose of quantum computing. This is most often referred to as decoherence, which is commonly prevented by very low temperatures and special coverings. Nevertheless, when compared to classic digital computing systems, a quantum computing system is inherently more unstable and prone to errors, so current work remains at the level of small-scale experiments. Theoretically speaking, hope is not yet lost for quantum computing. Remember that before things like ChatGPT, AI had seen periods of stagnation that were so bad they had a name, AI winters. Due to the superposition of qubits, quantum computers can execute a large number of operations in parallel without the need for manual hardware modification, as seen in digital computing. This also has a name, quantum parallelism, and we can enhance this with certain techniques. Constructive interference, for example, leverages the qubit's wave nature to amplify the desired outcome. And of course, we cannot forget the power of entanglement, which disturbed this guy so much he called it spooky action at a distance. Unlike digital bits, which are rather independent, qubits, especially entangled ones, can share quantum information and collaborate, much like the way neurons work.
So, can quantum computing recreate human experience? Sort of. Again, theoretically speaking, the parallelism of quantum algorithms can totally resemble the spontaneity of the human mind. History has shown that overcoming technical hurdles is only a question of time, and so there will become a time when quantum system can simulate consciousness. The real question here is the question of consciousness itself. What is it? You cannot build something that you do not know well enough, and unfortunately, this is the current situation regarding consciousness. As always, history may have the answer. Before the Wright brothers successfully replicated flight, this issue wasn't clearly understood, even with the realistic observation in the form of birds. Maybe the best way to figure out consciousness is by building it ourselves. And if you have a better way to do this, feel free to comment down below. Last but not least, thank you for watching.
Computer may be clever, but human beings are much smarter.
Yeah, definitely not.